morning. Always good to start with a black screen. Now, sometimes there is a question. They really haven't got the lights here, so I'm going to be mostly in darkness, like the screen. Sometimes there's a question of what are my talks about? It's not always obvious from the title. Today, I chose something different. It's blindingly obvious what this is about. It's about procedural programming. The curious thing is, why am I talking about procedural programming? Surely it's gone, it's dead, and we should be talking about functional programming and next-generational object-oriented programming and so on. Because it's dead. Well, I'm here to tell you that it's not. I'm also here to tell you that it's playing an important role in a number of other paradigms, and that we actually lost out an awful lot of stuff. There's a lot of stuff in classic procedural programming and its organizing model, primarily structured programming, that people think they know, but they don't actually know. Okay, so I want to explore that as we go through. And things about me, I edited this book a few years ago because I'm very much interested in code, but I'm also interested in the way that people do things and the way that architectures emerge and the experiences. In fact, almost to the point of this talk, there is this idea that patterns, to quote Brian Foote, are a blatant disregard for originality. Okay? The whole idea is that we know stuff. We know stuff already, we're just not very good at remembering that we know stuff or looking around our own history to discover that most of the things that we talk about have actually been solved. It's not that we all knew everything all of the time, it's just that it turns out in the heart of procedural, we actually find an awful lot of stuff that people are getting very excited by these days and dates back quite a way. So, procedural. When we normally think of procedural, we normally think old stuff, big slabs, monolithic. This is a photograph that I took earlier this year because my wife and I are clearly very romantic. This was taken on Valentine's Day. We grabbed the kids, it's just like, what should we do? It's Valentine's Day, let's get kind of romantic. Yeah, let's take the kids to go and see Stonehenge. They were quite impressed. They'd seen photographs of it, and you know, they were both like, actually, they're a lot bigger than we expected, Dad. You know, even once you've seen the photographs. Now, as with any presentation, I'm going to have to leave some stuff out because there's a huge wealth of what I could be talking about. And there is an art to leaving stuff out. You may wonder, where are all the tourists? Has anybody actually been to Stonehenge? Okay, where are all the tourists? They're all the way over there. That's the art of taking a good photograph. You show the bleakness of Salisbury Plain. But when people look at this stuff, what do they see? They see monoliths. Monolithos, the Greek for one stone, one big stone. This is what you see when you go into legacy code. You see these large, difficult-to-move stones, and you theorize, how was it that ancient primitive people were able to put together this code base? Okay, how did they do this? How did you get so many people to organize these monoliths? And everybody these days is like, oh no, I'm good. We've reorganized the stones. You know, hey, we've got microservices. Yeah, we're good. Yeah. Let me show you microservice architecture. This is what's actually happening. And none of this stuff is new. I mean, everybody's trying the same things all of the time. Doug McElroy in the 1970s, writing about the UNIX philosophy, captured an essence that we are trying to recapture with every passing paradigm, and which started in the 1960s. The UNIX philosophy: write programs that do one thing and do it well. Write programs to work together. There's two parts to it. People normally remember one part. Yeah. Oh, I've got something doing one thing well. Oh, it doesn't seem to fit with anything else. Let's just add some code to it. That is the decay that you saw, okay? It has been said that every program starts rococo and then becomes rubble. There's two parts to this, and this is something we're going to revisit later. There is a kind of mirroring here. But I want to take you back to the 1960s. I just referred to the 1960s. There's a lot of glorious stuff that happened in the 1960s. The 1960s was a time of change. And we think it's a time of change, but there are some things in the 1960s that are still with us. Okay? Some things just don't change. We've got the Rolling Stones. They are, against the odds, still with us. Okay? We have the fear of nuclear holocaust. I thought that was done, but no, it's back. It's a revival movement. The idea, I grew up during the Cold War, and it's just like, I was glad to see the back of that. This whole imminent fear of this stuff. I'm now teaching it to my kids, so it's something I feel I can pass on. And what else did the 1960s bring that we also still have? Me. There you go. That's me. Okay? Yeah, if you doubt the era, just look at the clothes. Right, so the 1960s, what else happened in the 1960s? Software engineering happened in the 1960s. The classic NATO conference in Garmisch in 1968. Now, a lot of people think that this meeting was where the term software engineering was coined. Well, clearly it wasn't, because they put it, it was already called this by the time people got there. 1968, this was actually coined, the term software engineering was coined by Margaret Hamilton, who led the team that wrote the Apollo guidance software. So this is all happening in the mid-1960s. She wrote this, and she coined the term software engineering because she felt that the people that did the software were getting looked down upon. And they used a number of different languages. Well, the key language they used was a language called MAC, the MIT Algebraic Compiler. And it was hand-compiled. If you're wondering what does hand-compiled mean, it is exactly as it sounds. Human beings looking at the code, because that's the only way you can trust that you're going to get the right stuff. You can't trust automation. Yeah, we have moved on a bit since then. But people would kind of take the code and then turn it into assembler, and then you'd have people cross-checking it. So at that level, that hasn't changed. We've got into this idea that maybe you check somebody else's work. So she was responsible for this. 1968 was a great year. Because 2001: A Space Odyssey came out, one of my favorite films, and it anticipated the moon landings. It was quite ahead of the curve. Now, the key thing here is, I want to observe, is the use of typeface. This is Gil Sans, which is a beautiful typeface, and very, very strongly influenced. It was developed within a year. 1927 was Futura. I used to think this was Gil Sans, but I did a quick check. The G's are different. And it's logical. Futura, this is in Germany. Futura is a German font. Gil Sans is a British font. So the typography of the 1960s is glorious and beautiful, and it's not something we should throw away. There's also some wisdom in here. I'm not going to say that we knew everything back in the 1960s, but it turns out that more people had the right idea than we give them credit for. When people think software engineering and they think this conference, they think, oh, it's all about procedural programming, formal proofs, and waterfall development process. Andy Kinslow, the design process is an iterative one. Okay, it's not the only point in the document that says this. This I find absolutely fascinating. Clearly something happened after the 1960s. Some people blame disco, some people blame flares, I don't know. Kinslow also had a great sense of humor and a great insight to go with his sense of humor. There are two classes of system designers. The first, if given 5 problems, will solve them one at a time. The second will come back and announce that these aren't the real problems, these are not the problems you're looking for, and will eventually propose a solution to the single problem which underlies the original 5. This is the system type who is great during the initial stage of a design project. However, you better get rid of him after the first 6 months if you want to get a working system. We also see other points here. Alan Perlis, the first recipient of the Turing Award. A software system can best be designed if the testing is interlaced with the designing instead of being used after the design. Now, I'm going to put some code in, because we're talking 1968 here. And I thought, okay, let's get a little bit retro. One of the languages that came out around then, Algol 68, was a fantastic effort in terms of language design. It was very much ahead of its time. People said they couldn't implement it. It was not possible to implement it. It was too big and it was too complex. I've looked through the language spec. It is currently smaller than the language spec for C. In fact, pretty much any language you care to name that you are using is larger than this. Okay, so our sense of what is large and complex has changed. But it introduced a really important principle into the mainstream concept of language design, orthogonality, the idea to compose different features, that everything is in some way regular. It had some rather nice, interesting ideas, so I'm going to calculate a leap year here. You could put spaces were not significant in identifiers, so is leap year, that's quite cute. And we also find, if you've ever wondered where the int keyword came from, it was Algol 68. Bool, ultimately Algol 68. Skip is basically parse in Python, but obviously we're going to start off with a default of false. Now I'm going to do this in a kind of a test-first style, because I was fascinated. I wonder if I can create a simple table-driven approach to just testing the leap year logic using Algol 68. It's absolutely trivial. It's lovely. So I'm going to create a proposition here. Leap year spec, years not divisible by 4 are not leap years, and notice what I'm doing here is I'm passing what we call a closure these days, but was simply an anonymous procedure. It returns void. Oh yes, if you wonder where void came from, Algol 68. In other words, if you are using a program language today, there is a 90% chance that you are using features that originally came from Algol 68. But I've never heard of Algol 68, you say. That's great, like you never heard of your great-grandfather. It turns out that you still have the genetic material, as do modern languages. Assert not is leap year 1967. Okay, so what does that look like? Oh, struct came from there as well. So what we've got is mode. It didn't like the word type, so they used mode of access. Proposition is a name and a void returning procedure that takes no arguments. So this is basically the way at the end of the 60s, and then also with the Algol 68 report in 74 that was refined to allow people to actually implement it properly, was the idea of this is how you do procedural programming. This is the essence of procedural programming. It is the procedure. You should be able to take procedures and pass them around. Okay, that is fundamental to procedural programming. A lot of people got very excited about higher order functions and first-class objects recently. It's kind of sweet. If they knew their history, they might not be quite so excited. So now I can go ahead and I can do this, and I can run a test against it. Let's test the leap year spec. Turns out the test function is here. Anything I want to point out? Oh, those of you who are using Bourne shell and its derivatives like bash, if you've ever wondered about do and odd, yep, they come from here. Didn't have dot notation, they used of instead, but they did use square brackets for arrays. Let me think, anything else there? Right, so let's build this one up. So here's an interesting one. The whole of the body of my procedure is actually an expression. I don't need to put a return. In fact, there is no return in Algol. We'll discover why in a moment. And I can just build this one up. Okay, assertion at a time, and it's all quite readable. This all makes kind of sense. Equals does mean equals rather than equals equals. So yeah, this is quite cute. This is actually surprisingly easy to write. Now, there's a couple of other things that we can do here. Maybe I want to make this more data-driven rather than just passing in blocks of code to run. I could make it more data-driven. So perhaps I want to write something like this. Years not divisible by 4 are not leap years. So with 2017, 2001, 1967, and 1, expect false. And you see, this is quite nice. Slight change there. Let me think. Types, resizable arrays. One thing Algol 68 fortunately did not pass on to most languages is that it is 1 counting. You count your arrays from 1. I'm sure this makes Americans feel very comfortable because they think that the ground floor is the first floor. Whereas everybody else knows that's an off by 1 error. You count from the ground floor. 0, 1 above ground, 2 above ground, 3 above ground. This makes for some very interesting international conversations sometimes. I'll meet you on the first floor. Yeah, never made a mistake with that one. Okay, so the test driver for this is a little more involved. I'm not going to go through it in detail, but I want to draw your attention to some of those radical features that people have thought are more recent. Not the fact that there's a statement there, but the fact that there's declarations after statements. The idea is that a declaration is a movable thing. This has ultimately made its way into C++, for which one of its progenitors was indeed Algol 68. Bjarne was very strongly influenced by it. What else can we say? Yeah, you can declare anywhere, including an if statement. I've noticed some Go programmers got very excited about this 1960s innovation recently. Basically, Go was invented in the 1970s. Every feature that Go, if you think Go is a modern minimal language, it was invented in the 1970s. It just took 3 decades for somebody to actually put a syntax to it. Go is effectively a procedural language. We find that it is not particularly object-oriented, it's not particularly functional. It might use the word func, but that's the influence of the 1970s. It's more a case that it is a classically procedural language in the Algol 68 tradition, including its concurrency model. We'll come back to that a little bit later. What else can we put in? Oh, yes, you've ever wondered where the compound assignment comes from? It comes from Algol 68, although we obviously dropped the colon after a while, in line with the equals for assignment. And this whole point is that statements and expressions are interchangeable. There is no concept of difference here. So I can easily have an expression that is conditional, that contains loops. There's also a shorthand, which is actually, curiously enough, probably slightly more elegant than the Elvis operator that we find in C-influenced languages. Although I still quite like the fact that we can use if and else to make it more explicit. So there's a lot of stuff going on here, which I think is absolutely fascinating. A lot of people don't realize this is how procedural programming was supposed to evolve. I'm not going to make a claim, by the way, that this is when TestFirst Development was developed. That was the 1970s, okay? You've got to get your decades in order here. That was the 1970s, and the development of Orc, Aho, Weinberger, and Kernighan were the 3 people responsible for that. We instituted a rigorous regression test for all of the features of Orc. Any of the 3 of us who put in a new feature into the language first had to write a test for the new feature. But what I am trying to make a point about here is that, as in common with many ideas that become popular, there is obviously an original vision that a few people share. It is crystal clear, it is obvious, it is normally complete and fully formed. We see this with microservices, we see this with Agile, we've seen this with object orientation, we're seeing it with functional programming, and yes, also for procedural programming as well, as I want to make the case here. I've talked about other paradigms, and I thought it's time to give procedural programming a little bit of love and to shine the light on it. Let's talk about testing a bit more, because we can actually see a few other things here. Going back to the 1960s, Alan Perlis also said there's no such question as testing things after the fact with simulation models, but that in effect the testing and the replacement of simulations with modules that are deeper and more detailed goes on with the simulation model, controlling, as it were, the place and order in which these things are done. If you're struggling to parse that, let me just replace that with mock objects, which were invented by Archway Tube Station in London in 1999, or in 1968 at a meeting. Obviously, they did not have the detail or the insight to elaborate the details, but the germ of the idea was already there, this idea of perpetual elaboration. I'm going to dummy something and then elaborate it. But also there's something here. We're going to talk about mock objects, and perhaps we should talk about objects. It turns out that psychotherapists, so here's a lot of objects. Psychotherapists are utterly obsessed with objects. Actually, they're utterly obsessed, is my experience. But what I want to refer to here is we've got objects, we've got a stack. Oh, everybody loves a good stack, so let's put a good stack up here. The word simulation came into that previous thing. Here we go. This is Simula 67 code. And obviously the clue to the language's age is in its number. So it's 50 this year. And we find a number of things here. I haven't put any virtual procedures in here, but virtual comes from Simula. This comes from Simula. If you're using any of those languages that use these keywords, this is where it all comes from. And so I've got a very simple stack here. And we can see all the basic bits and pieces are already in place. But where did Simula get its ideas from? Simula 67 was an extension of Algol 60. It was described by many as an improvement on many of its successors. Okay? There are ideas in there that we can still mine. But there's something in the heart of Simula that goes right back to procedural thinking. Now, this is the 1960s. So what have we got? We've got procedural thinking. That's assumed, where a lot of people are still programming assembler. People are not necessarily taking the Algol path, because Algol was primarily a European initiative, but Fortran, for which John Backus, well, he didn't exactly later apologize, but he came up with good stuff later in his life, and COBOL were driven by large companies, in this case IBM, and naturally grabbed the mind share. But there were ideas around, and not everything that was around was necessarily going to become popular at that point. We see also, this is the era of early Lisp. The Lisp manual was the early 60s, although the language was effectively invented in the late 50s. I think it's one of the best written examples of how to introduce a language, because they introduced it with the implementation. I thought it was absolutely brilliant. Because you couldn't port stuff, you know? There's no concept of open source or anything like that. So we're going to tell you how to build a Lisp machine whilst we teach you Lisp. And it's very cool. So there's a lot of stuff. So this is the 1960s. What have we got? We've got procedural programming. We've got object-oriented programming. We've got functional programming. Yeah, things have really changed in the last 50 years, haven't they? It's like we've moved all this way, and we're exactly back where we started. Well, not exactly. We have a better understanding. We've tried stuff out. But basically everything that we now do, or the majority of what we now do, was already in play in some form. So I mentioned earlier on that there was a kind of idea, procedural programming, when we think about it, we think about its organizing principle. And this is the language of structured programming. Structured programming kind of kicked off in the late 60s and dominated people's thinking and discussions in the 1970s. This is my copy of, I collect old books in case you're wondering, and I like photographing them as well. They're a lot easier to photograph than people. This is my copy of Structured Program, Ole Johan Dahl, Edsger Dijkstra, and Tony Hoare. Dahl was one of the co-inventors of Simula 67. And people think they understand what structured programming is, but this is a collection of essays from the 1960s and early 70s. When you dig into it, there's some really interesting stuff. Some of it is a little dated, some of it is still ahead of its time, and some of it is, oh, that's where this idea came from. And people often think, however, when they talk about structured programming, they have a simplified view. They say, oh, structured programming, isn't that just all about the goto? Yeah? This is the classic problem. When an idea becomes popular, it becomes simplified in some way. It becomes diluted. And everybody said, this whole paradigm is about that. Yeah? I've had conversations with people about objects, and they're there going like, yeah, but where's the manager object? It's like, no, really, it's not about that. Yeah? In fact, it's almost exactly not about that. Yeah? So we end up, you see, and by the way, in the heart of goto, there's OO. Okay, that's just a coincidence. Actually, there's a little bit more to this. We'll come back to that. So the thing is, when people think about goto, they start thinking, oh, Dijkstra, the classic letter, comms the ACM, once again, 1968. Goto statement considered harmful. And people, this is the launch of what is known, well, this is a kind of standard phrase, isn't it? Something considered harmful. These days, if you want to do anything and you want to draw attention to itself, you use it's standard clickbait. It's just like X considered harmful. Okay? It's just like, yeah, I'm going to write a blog. You know, how do I write a blog? Introduction to something or other. Oh, that's really that's really boring. Okay, let me reframe that as something considered harmful. Let's find now suddenly you get all the your web page. You're getting the hits now. Fantastic. Okay, this is effectively what is known. There's actually a term for this. Now, one of the things that I do is I have a page on Facebook called Word Friday, where I share an unusual word every Friday, and the rest of the week is linguistics and words and other stuff of interest. One of the words that I came across a few years ago and put a definition up for is a snow clone. So this is quite a useful word. A snow clone, a cliched wording used as a template, typically originating in a single quote, such as X considered harmful. These aren't the X's you're looking for. X is the new Y. It's X, but not as we know it. No X left behind. It's X's all the way down. All your XR belong to us. These are examples of snow clones. Okay? So we might say, okay, goto statement considered harmful by Edsger Dijkstra. He launched a snow clone. Actually, he didn't. This is the original that he sent. A case against the goto statement, it's much more modest. It's much simpler. I'm offering you something here. It turns out that the editor of communications of the ACM for that issue was Nicolas Worth, the inventor of Pascal. And what Worth did is he decided, well, these days we call it clickbait. He changed it. You know, it's just like a case against the no, I need something snappier. I need something that's going to get the hits. You know, people are opening up their comms of the ACM and they're going to look down the goto statement considered harmful. Excellent. We can change that. So I want to take this a little bit beyond this, but as an idea, this whole go-to thing, it still resonates. This is the Taligent Guide to Designing Programs, 1995. They pull no punches. A go-to completely invalidates the high-level structure of the code. There's no kind of doubt about what they think here. But what are they saying here? A lot of people have never had the experience of working with go-to ridden code. Okay, maybe if you've done some assembler, you'll have encountered it. Or maybe you've come across some fairly treacherous old C. My experience was that this is my confession to you, once upon a time I programmed Fortran. And all of these discussions were current then. And the use of goto and all the rest of it. And yeah, goto doesn't have to be spelt goto. Goto can be spelt in a number of different ways. When we talk about the idea of the discipline of structured programming, the discipline of structured programming is the idea of a single entry into a block and a single normal exit. You may exit via abnormal means, but a single normal exit. And people often talk about the multiple exit thing, but they never understand, what does multiple entry look like? It looks like this. This is known as Duffs Device. It is an approach to unrolling a loop. It was used in the early 80s, I believe, in some telecoms code at AT&T. It is astonishing and scary. I remember the first time I saw this. This was a real WTF moment. It was just, you can do this? If you want to do this in Java, you can't. The language designers decided, no. C#, no, you can't do this there. In fact, C is pretty much the only place you can do this. Tom Duff captured his feelings. I feel a combination of pride and revulsion at this discovery. The ability to jump into the middle of a block. So actually what we've got, if you've ever wondered, so let's go back to the 1960s. 1960s was when Star Trek was first aired. And Star Trek introduced to the public the idea of teleport. And always that question, what happens when you teleport into something in the same place? Well, this is what happens when you teleport a do-while loop into a switch statement. They merge in the same place, okay? And it's a horrible, ghastly thing that is both revolting and elegant and pride-worthy. As Tom Duff says, many people have said that the worst feature of C is that switches don't break automatically before each case label. This code forms some sort of argument in that debate, but I'm not sure whether it's for or against. Now, the point with this stuff is there's an idea, when we talk about the organization of procedural programming as a discipline of thinking and a discipline of programming, there is an idea here that what is a block? What is a statement? The idea that I can substitute one thing for another is a very profound idea, and it is about this idea of single entry, single exit is part of it. So I'm going to render this. I'm going to bring this one up. This is, I think, the only piece of 21st century language we're going to actually include. So this is Groovy. This is the leap year thing that I showed earlier on, but done in Groovy. Now, one of the things that Groovy allows you to do is say, okay, the last statement in a block doesn't actually have to have an explicit return. We can basically say that the block comes to equal that last term. So I can easily do that, which gets me the Algol 68 code that I had earlier. But some people are not comfortable with this logic. They like to see the ifs spelt out. They don't like the ands and ors. So they go about it and they do this. There's another way of doing it that also does ifs and returns, and it looks like this. One of these is structured, and one of these is not. One of these is elegant, and one of these is popular. This is the most popular one. I find myself always dealing with people who say, oh, yeah, but Eclipse made me do it, and stuff like that. And the point is that there is a qualitative difference. These will actually generate the same underlying code. This is not a question of what you're generating in terms of the code. It's to do with the model of reasoning that we bring to it. And that's the different thing. If we look here, if I try and do the replacement, I can only do it in one place for this one over here. Over there, every branch, there's a tail return. Every branch exclusively ends as the result of the function. Okay? There is an exclusive path through this, and it is simple. In fact, I'm going to put the return back in there because that just makes it look uncomfortably irregular. if we want to understand block structure and what people were actually trying to talk about, it turns out that what they were talking about was the alignment of control flow and data flow. Now, if you frame it like that, you get a lot more people on board because they, oh, yeah, I'm totally about the functional. And that is about the alignment of the control flow and the data flow. But they didn't articulate it like that because that language or model of reasoning did not yet exist. But the block idea is really important. People often assume, well, these days, I hope we all indent our code. I say I hope because I don't make that assumption. I find a lot of self-taught programmers that don't use IDEs do not indent their code and regard that as some personal point of style. You know, oh, that's just the way I do it. That's my style. It's just, no, it's unreadable. And I mentioned Fortran earlier on. I worked on my boss's code. He didn't believe in such nonsense as, you know, indentation. It was an affectation as far as he was concerned. When I indented his code, the number of bugs I found was astonishing and frightening. But let's get back to this. Let's understand the nature of block structure is the idea of folding concepts away. It's about folding complexity. It is the idea that I'm going to just fold away all of the second level stuff. I'm going to focus on the first level stuff. So can I reason about this function and this function without understanding the content of each branch? And the answer is no in one case and yes in the other. On the right-hand side, I have something that is visually honest. It says, this is a function that is a four-way decision. And does it look like it? Absolutely. Okay? Mutually exclusive paths. On the left-hand side, I've got surprises and mystery. Obviously not in a piece of code this long. I'm going to say this is a non-challenging piece of code, almost any way you write it. But it's when it gets larger that we struggle. The point here is that what is going on the left-hand side? On the left-hand side, this is either we're going to return false, but we've got a bunch of guard statements to check for bad cases. These are not bad cases. This is the definition of a leap year. It's perfectly good. These are not exceptional. These are not guard clauses. It's a misuse of the guard clause idea. Or it's we're going to return false, but we've got 3 optional pieces of pre-processing to do. Is that what we're doing? No. The point here is you cannot tell unless you go into the next level. The idea of a block in procedural programming is to encapsulate a bunch of stuff so that you don't need to know what it does. I don't need to know that there are returns in there, continues in there. In fact, I can put anything I like in that and it won't change on this side. That is the basic idea that they were struggling. That is what we mean by this stuff. So we put this stuff back and it turns out that this is the one that we want to focus on. That's what we mean by structured programming. And as they observe, one of the most powerful mechanisms for program structuring is the block and procedure concept. Now this, it turns out, is where a lot of ideas stem from. There's this simple idea that when we are organizing, you've got messy procedural and tidy procedural. The structured view was to compose any logic to describe what it is that you need to do. All you need is sequence. So sequential composition, I have one thing and then another. I need to be able to make a decision. I need to select between alternatives. And I need iteration. If you replace iteration with named abstraction, you can get rid of iteration and have recursion. But the idea here is that let us not assume that that is available to us. Sequence, selection, iteration. And this was proven to be basically all you needed. And what you did is you organized your code base according to this, then over a series of procedures. Now, if we look at a characterization of this as an architecture in Basclam's and Kasman's software architecture and practice, they refer to this style as main program and subroutine. I have never met a programmer who has referred to this style as main program and subroutine. I think it's a really good characterization that they describe, but sometimes people struggle for names. What do we call this procedural approach? We could call it procedural. No, that's too obvious. Let's describe it by what it's no. At some point, we're going to have lunch. Oh, okay, does that mean first course, second course, and dessert? No, we don't describe it like that. We call it lunch, okay? So there is a notion here that there's also the fact that people didn't think of this as a programming style because everybody was doing it. This was the mainstream of programming. Yeah? If everybody's doing it, you don't have a name for the style. You know, what's your programming style? It's programming style. It's the way we program. But what does it have a name? Yes, it's called programming. You know, what are you talking about? Yeah, if you went to most mainstream programmers back in the 70s and 80s, there was no concept of alternatives here. Okay, regardless of the naming, we understand it's accurate, if a little long-winded. They characterize this architectural style. The goal is to decompose a program into smaller pieces to help achieve modifiability. Yeah, I'm not aware of any architectural style that doesn't have this as its mandate. So this is kind of noise. You know, you don't get people saying, we've come up with a new paradigm. The idea here is to cause problems for maintainability or to not allow you to decompose. That's not how people do work. Okay, so that's a noise statement. This is more meaningful. This is the vision. So I'm not going to say that procedural programming is what you want to do everywhere. But if your problem looks like this, then this is the way to start thinking about it. The idea is that we have many paradigms because problems have many shapes. A problem is decomposed hierarchically. Each paradigm that you encounter has a philosophy. It says, here is a truth that we hold for this kind of thing. And this is what we're going to do. We're going to decompose things hierarchically. Okay, there you go, main program, subroutine. That's what we're going to do. We're going to create a tree of control, a tree of decomposition, top-down programming, stepwise refinement. These are all terms about how we organize this. We have an objective that the code wants to achieve. You can see this doesn't necessarily work for event-driven code. Great, we've already discovered now a style that it doesn't work for. But if you have an objective and you can decompose it, algorithmically is quite a good one, then you've got this. And it goes deeper than this. The structured programming school, there was actually a way of characterizing these things. It wasn't just about throw subroutines together. People came up with wonderful names for stuff. There was a whole vocabulary for this. This is the afferent branch, the transform branch, the efferent branch. These are good terms to throw into a conversation if you want to confuse your colleagues. You know, if you want to kind of, you know, it's just oh yeah, but I was looking down the efferent branch of the code. Okay, what's he talking about? I think he means output. Input, process, output. Okay? Oh, we've never seen that before. Yeah, but that's too obvious. Again, we have to come up with names that confuse people. You can't call that the input, the process, and the output branch, because then people know what you're talking about. So what we're going to have is the afferent, transform, and efferent branch. Yeah, we're going to raise it a bit. Yeah, make it sound more computer sciencey. Now, obviously, we don't always call it, you know, so we see this philosophically. And then we see further characterization here. This tells us a little bit more about what is it that makes procedural. There is typically a single thread of control. That will come back to haunt us. And each component in the hierarchy gets this control. So it's the passing of control. And in the structured world, we view that with respect to selection, or sequence selection and iteration. The passing of control optionally along with some data from its parent and passes it along to its children. We have a strict stack discipline for how control and data flow to and fro throughout the code base through this hierarchical decomposition. Yeah, so subroutine, perhaps we don't use that term anymore as much. Maybe we call it procedure, maybe we call it function. Curious. If I took away mutable state from procedural, what would I be left with? What's it called? Functional programming. Yeah, if you take away the mutable state and you can still pass procedures around, you have higher order procedures, now let's call them higher order functions, and so on. And it's the thought, this was all there. Oh, that's interesting. What I find interesting, what validates or strengthens a paradigm is when you can arrive at its conclusions from multiple paths. In other words, it's not just one way of thinking. It's like you can reach a functional view of the world as you can reach an object view of the world via taking many different roads. And it's just like, same conclusion. That validates it in that sense. Now, of course, this beauty of this hierarchy is that, of course, it doesn't look like this. In real programs, you end up with mixing of levels. Okay? You end up with fan in and fan out. Fan in, what do we call that? We call that reuse. Okay? Here's the thing, I've used it in more than one place. Okay? Fan out, that's a classic decompositional approach. And also we get recursion. Direct recursion and mutual recursion. So, the tree's looking a bit messy. And this does also tell us that there is a limitation sometimes to how we think about things. As Tony Hoare observed, you cannot teach beginners top-down programming because they don't know which end is up. And I think that is wonderful because the idea is when I'm trying to establish what is the objective and goal of this program, you know what, that is non-trivial. We've created whole methodologies to try and answer that question. What do we mean by this? Perlis also had this wonderful observation: everything should be built top-down except the first time. Which I think is a lovely way of putting it. It turns out that top-down is a great way of describing something. It's entirely reasonable. You can actually show somebody and decompose an idea top-down, but that may not be the same as the story that was used to create it. Yeah? But it's a great way of describing it, because people go, oh, yeah. Why did they take so long to develop it? It's so obvious now they've said it. That's how you know you've got something really good. Top-down is a great description model. So this presents us with a bit of a challenge. How shall we organize our procedures? Into the breach steps David Parnas, 1972. What else happened in 1972? Apollo 18 never left the launch pad. There was no Apollo 18. Apollo 17 was the last one. So that's the end of the moon landing story, but the beginning of modularity. Yay! Right. We propose that one begins with a list of difficult design decisions, or design decisions which are likely to change. Now, here's an interesting question. How do you... This one hasn't changed. Okay, this is 1972, 45 years ago. How do you know that something is a difficult design decision? Well, I don't know. We keep spending hours discussing it. There you go. We can't agree on something. There you go. Yeah? The fact that you cannot agree with your colleagues about something is a really strong, big arrow saying, we're not sure about this. It is not an opportunity for you to beat your colleague or come up with the killer answer. It is an opportunity to step back and go, oh, that's interesting. Maybe the answer is not so obvious. Maybe there are multiple ways. Maybe the way that we describe it now is good in one way, but in 6 months the world moves on, the frameworks moves on, the performance requirements move on, and we have to change somewhere else. So let's structure our code according to this level of indecision. Each module is then designed to hide such a decision from the others. And that is a kind of a classic way of thinking. This was the overlay onto classic procedural programming. This idea of modules and modular programming sort of came along. Again, it did not get adopted into the mainstream as readily or as comfortable as people would have hoped. And indeed, the mainstay of programming in the 70s, something like Fortran, did eventually get modules, but it wasn't until the 1990s that it did so. It was never one to hurry things. But one of the most common decisions that we can make concerns data structuring. Barbara Liskov, recipient of the Turing Award in 2009, she was one of the key individuals, this is 1974, key individuals in really motivating a style of programming organized around data types, but not simply structured data, but abstract data. Abstract data type defines a class of abstract objects which is completely characterized by the operations available on those objects. A programmer is concerned only with the behavior which that object exhibits, but not with any details of how the behavior is achieved by means of the implementation. Implementation, yep, there we go. 1974, again, what happened in 1974? The Algol 68 report was finished again. People weren't doing much interesting stuff in space on the other side of the Atlantic, but the Soviet Union was doing some very interesting stuff. And there's a whole load of stuff that was going on in code. This was really quite exciting. Now, what else happened in the 1970s? C happened in the 1970s. So it turns out you can actually mix this approach in with C. So let's go back to our stack of books. And I'll just have it as a stack of strings. Let's update this to ANSI C. And what I've got here is a forward declaration of a thing called a stack, okay, and a regularization of the name. And how's that going to look? Well, we're going to create a stack, and we're going to be able to delete a stack, okay? Notice there's no detail of what a stack looks like. The idea is that I've simply said, let's talk about how you work with the stack. Don't worry about the details. This is in a header file. And here are the common operations. There's going to be a stack of strings, so const char star. I'm going to push, I'm going to pop. It's a pure pop. I'm not returning anything from that. Depth, I can query that, and I can also find out the top element. And we're also going to allow people to link this into and compile this into their C++ code, so we put a bit of noise in. Okay, so what does the implementation look like? I'm not going to focus on the implementation, I just want to show you what it looks like. There we go. So here's an implementation, very simple implementation of that stack protocol. But I can also change the implementation. That's implemented in C. What flavor of C? That is definitely C89, C8990, depending on how you want to count. Yeah, it's not later. And this is C++. So I've got exactly the same I've got exactly the same interface, it passes exactly the same tests, but not only have I got a slightly different implementation, I've ended up using a different language. That is what was meant by abstract data types. It's that abstract you can change the language, but you're still focusing on something. That is, how do I do this? However, there is a small difference between these pieces of code, and it's to do with memory ownership, and this is a struggle. And a lot of people think, okay, procedural programming, that means you're always going to manage your own memory. These two are different. The C version leaves the question of memory management slightly open. The C++ version encapsulates it. So I've talked about the 1960s, I've talked about the 70s and beyond. I want to go back a little bit further. Okay. Shakespeare was one of the first programmers that I know of in England, and he had a bit of a problem. There weren't any computers. It makes it really difficult to program things when there are no computers. In the Elizabethan era, the late 16th and early 17th century, there was a lack of computers. However, Shakespeare was a big fan of the actor theory, so he used actors to do this. Again, centuries ahead of time. But he had to encode his concepts and his models of programming carefully into his plays. And when you review his plays with this in mind, you end up with a completely different worldview. So for example, Hamlet. The Tragedy of Hamlet, Prince of Denmark, is actually a play about memory management. We can see it from one of its most famous lines, "To be or not to be, that is the question." You see, Shakespeare is vexed by this question. This is difficult. How are we going to manage the memory? Now, we've got Ophelia steps in and says, "'Tis in my memory locked, and you yourself shall keep the key of it." Ophelia is really big on malloc and free. New and delete. She says, okay, you manage your own memory. I trust you with this one. That did not work out well. Hamlet's a little more, you know what, I think garbage collection, what about that? Yea, from the table of my memory, I'll wipe away all trivial fond records. Okay? So we see here that this has been plaguing people as a problem for a very long time. Encapsulated versus non-encapsulated, explicit memory management versus the idea of garbage collection or something that is managed. And there is a thought that sometimes people, again, as I said, associate procedural programming with the unmanaged approach. But I'm going to say that that is purely historical, or rather one view of history. Algol 68 had garbage collection. Simula 67 had garbage collection. These are 1960s languages. And at the time, people assumed that it was only Lisp that had it. No, garbage collection was a thing. The problem is we did not have the resources available to make a good go of it for anything other than academic programming. The point is that at that point, to try and introduce this into limited memory, limited processing environments was seen as a luxury. If we revisit procedural programming from that point of view, and we see actually, yeah, we could do this, and we do this. Because this is where it gets kind of interesting. There is an idea that when we look at this, there's another concept that is going on. How old is this idea of capturing state and moving it around? How old is this idea of organizing your code with units of state associated with procedures? Well, it turns out that part of structured programming, part of the procedural paradigm, as it was envisaged, included a rather interesting idea called hierarchical program structures. A procedure which is capable of giving rise to block instances which survive its call will be known as a class, and the instances will be known as objects of that class. So there is this idea that the block and procedure concept is the powerful idea. What if I were to pass to you a block that contained data and its own procedures? Again, we can call that a closure, we can say that there's a lambda-ness happening, there's all kinds of stuff here. That was the essence of this. In fact, I can even represent that in JavaScript. I can say, okay, I'm going to create a new stack. I'm going to have a private representation. It's so private you can't even reflect on it. It's proper private, because it's a local variable, items. It's going to be an array. And then I'm going to return to you a collection, basically, of named lambdas, depth, top, pop, and push. that operate on that. And so what you are given is something that is truly a separation of implementation from the public face. You are only presented with something through which you can name methods. This is effectively a realization of that block idea. This is one of the purest forms of object orientation that you can have. And we can mess about with the implementation and still get it passing the same tests. Now, there's another thing people associate with object orientation, and it's known as concatenation. Well, it isn't, is it? It's called inheritance. But back then it wasn't called inheritance. It was called concatenation. The idea that I can concatenate one block with another and that they end up with the merger of all of the procedures and all of the state together was the basis of inheritance. Concatenation is an operation defined between two classes A and B, or a class and a block. You can have a freestanding block and just inherit into that block, mix-in style, and results in the formation of a new class or block. Actually, we can do that with there's this idea here. Concatenation is a merging of attributes and the composition of their actions. We can actually show this if I just tweak my JavaScript code a little bit and add in the idea of a base class, and add in the quality of something being stackable, and then add in the idea that you add things, you concatenate onto the existing base, you add in new methods. Okay, what does that look like if we do inheritance? Or rather, concatenation. I'm going to take an empty object that does nothing, I'm going to make it stackable. So that's how I create a new stack. Okay, let's make it clearable so that we can actually clear all the elements of the stack as well. Oh, what's that look like? Well, that's clearable stackable. Okay, so we've actually got inheritance is an act of composition. Okay, it turns out that it's a fundamental concept here, and we can actually make it a true composition in the functional style with a reduction. So it now means inheritance is equivalent to composition, which is quite cute, and encapsulation is equivalent to passing a block. So here's another old idea. A construction principle of concept hierarchies is called abstractions. We concentrate on features common to many phenomena, and we abstract away features too far removed from the level we're working at. So here's an interesting idea. This is all part of the structured programming vision of how you work with procedural programming. This is the bit that people forgot. It's the third part of the book. The book has three parts. Everybody focuses on the first part, which is about control flow. The second part is on data structuring. The third part is this. Okay? And what we discover is that people's view of structured programming as the organizing discipline for procedural is incredibly narrow from a historical point of view. So hang on, if we're talking about concept hierarchies, that leads to type hierarchies, substitutability. Barbara Liskov again, for whom the Liskov substitution principle is named. And she described this type hierarchy as composed of subtypes and supertypes. The intuitive idea of a subtype is one whose objects provide all the behavior of objects of another type, plus something extra. And then she characterizes this. What is wanted is a property here, substitution. If for each object O1 of type S there, let's see it in action. Let's have a non-duplicate top. Let's mix in a non-duplicate top. Let us imagine that we want to make our stack so that if you add in a duplicate top, then it doesn't add it, okay? So if you add in the same element twice, it says, oh, we're not going to have it. Okay, so let's just add that in. Let's mix, and we're going to mix that in. I'm going to write a simple test here. And the test is a non-empty stack becomes deeper by retaining a pushed item as its top. We're going to create a new stack. We're going to push build stuff, and then we're going to push 2017. We're going to push 2017. So we're going to push 2017 twice. The depth should be 3. The top element should be 2017. Okay. If I make a stack, if I compose a clearable stackable object, then this passes. If I then make it a non-duplicate top, this fails. In other words, it turns out that the Liskov substitution principle, as an extension of concept hierarchies, what Barbara Liskov was focusing on was this. It's a testable property. For all programs P defined in terms of T, the behavior of P is unchanged when O1 is substituted for O2. Now, that's not the 1960s. This is the 1980s. But what we see is that flowing from that original vision of we're going to organize procedures and we're going to allow concatenation between blocks in a way that allows you to organize concepts based on abstraction, we see all of these ideas coming together. But I want to talk a little bit, I want to end the talk by saying, okay, this is all very well, this is historical, but what does that mean for the present tense? Well, first of all, it means that these ideas are old, they are testable, they've been around. Most of the things that you're seeing in programming languages already probably existed, and that's okay. But let's take a different view. Let's understand what is the future of procedural programming, because it turns out that procedural programming is still one of the dominant approaches, not always applied correctly. So that's why people use the term procedural to mean bad. It's a long way of saying bad. When people say, oh, that code, it's so procedural, they're not saying nice things about it. Okay? Because it's being applied out of its context, where it tells you that it's got a problem with context. And there is a different vision I want to offer you. This an idea I mentioned earlier on, this multi-paradigm approach. The idea that procedural is perhaps very good at describing things that are small. It's not always the right thing. There's lots of other things that are good at describing things that are small. But what you need is a separation. And David Galerton, who was one of the key developers of the Linda system, talks about coordination languages. This is from 1992. We can build a complete programming model out of two separate pieces, the computation model and the coordination model. And this is something that we have been moving towards and where we can see the future of mixed paradigms, including procedural, going. Historically, we had Nicolas Worth writing, this is the title of a book that he wrote on structured programming, Algorithms plus data structures equals programs. We are going to refine this. Coordination plus computation equals programs. And we see that this idea has been around for a very long time. This is the original Make program on Make, the Make build system. If you look at Make, Make is a declarative system. As observed here, the Makefile language is similar to declarative programming. Its main backbone, its coordination model, is declarative. You set an objective, relationships between files. And then the computation model is procedural, it's regular script. So in other words, it acts as a framework in which to hang your scripting code. And of course, this can be, if you've always assumed that state change was okay and sequencing was always guaranteed, this is going to confuse you because this is the imperative model that we're coming into conflict with. But this vision of something bigger actually gives us a very different way of looking at things like concurrency. So let's understand, I mentioned earlier on there was a problem with this idea of single thread of control. I want to present to you food for thought, given that it's lunch, food for thought. This is a simple quadrant diagram that characterizes what you need, how you need to think of sharing of data with respect to concurrency. Your data can be mutable or immutable, and you can have it shared or not shared. There are 4 quadrants, okay? One of them is difficult. I'm going to use nature's color of danger to give you a clue here, okay? The color of blood. Blood is on your code, okay? This is the hard bit. This is the synchronization quadrant. If your data is mutable and shared between threads, you will have a hard time. If it is immutable, you will have an easy time. If it is unshared, you will have an easy time. But the minute you share it and change it, you will have a hard time. But we are drawn like moths to a flame to the top right-hand quadrant. 3/4 of it looks easy. Oh, that's too easy. Let's move there. But why did we end up here? Unfortunately, we ended up here because of procedural. Because procedural soft space, its comfort zone, is a very simple idea. The world is sequential. Sequence, selection, iteration. We do that. That means we're on the left-hand side. For decades, we were on the left-hand side, and it was a matter of constraint and efficiency that we're on the left-hand side, and we favored the mutable model. That's closest to the machine. So when threads come along, we find ourselves moving rightwards, and we go from the top left to the top right, which is where all the pain happens. I was like David Butenhoff's observation about mutexes. I've often joked that instead of picking up Dijkstra's cute acronym, we should have called the basic synchronization object the bottleneck. Yeah? I want you to think about that conversationally. What you need here in this code is a bottleneck. Yeah? It doesn't sound quite so good. Mutex makes it sound all kind of like positive and computer sciencey. It's just like, oh, we need a bottleneck here. Not so good. So we actually find the original vision. Computation model allows programs to build a single computational activity, a single threaded step-at-a-time computation. That is the idea, is what you have is little pieces of computation, and then you coordinate. This idea of a coordination language is, the model allows you to create a larger ensemble. And one of the earliest examples we have of this dates back to 1964. Doug McElroy again. we should have some way of coupling programs like garden hoses. Screw in another segment when it becomes necessary to massage the data in another way. This is the invention of the UNIX pipeline. It took another 6 years to pick the character. Okay, 1970. Ken Thompson did that. But this is the basic data flow architecture. This is the coordination model for Unix. Okay, the classic Unix model is we have procedural shell and procedural C code, and then we have a coordination model that is the pipeline. And we can extend the pipeline. We can do lots of things. We can talk about pipelines as a discipline. We can say, well, you have perhaps a number of items you can keep in there. So whether it's bounded, it's buffered, it's asynchronous. So all these ideas are fundamental there. We can change the numbers. You can have infinite. Well, you can't, but unbounded, don't have unbounded queues in your code, it's bad. But unbounded, buffered, and asynchronous, if you make it 1, it's bounded, buffered, and asynchronous, we call that a future. Futures and promises come out of this model. And if you make it 0, you end up with the default channel model of Go and other languages that use this, like Occam, and indeed a classic coordination model. This was one of the ways of reasoning about all of this. Tony Hoare, again, communicating sequential processes. We take sequential processes because it turns out we're really good with sequence, and we coordinate between them using channels. This is 1970s. Okay, the book was 80, but the original CSP model was 1970s. People have come to the actor model, which relates to this, and CSP again recently. This idea of paradigm mixing through coordination and computation makes sense of where procedural programming is going to be with us in years to come. So, on that note, if you're going to use the word paradigm, I always direct people to this paper. This is, that's a deep sound. Paradigms program, Robert Floyd, Turing Award winner in 1979. He's the guy we can blame for using the word paradigm and introducing it to software developers. And his perspective was not that we should pick the best paradigm. He had a very different view. I believe the current state of the art of computer programming reflects inadequacies in our stock of paradigms. Our knowledge of existing paradigms, in the way we teach programming paradigms, and in the way our programming languages support or fail to support the paradigms of their user communities. This was true in 1979, and I want to say that it is still true now. So that I would urge you to go back and revisit the basic ingredients of something like procedural programming, or a paradigm that you learned and rejected and forgot and decided this is ridiculous. This is an old idea. This is a deep idea, and this is how we're going to be taking this forward. I hope that's been useful, or at least provocative. Thank you very much.